Hello, my name is Rachel Malecek, and I'm a grad student from Louisiana State University. Today we're going to be talking about studying the low-lying states of boron 9 with the super Angie split pole spectrograph. First, a little motivation of why we're interested in boron 9. So boron 9 is a light neutron deficient nucleus that is very unstable, even in its ground state, and this makes it very difficult to study. Decades of previous efforts have tried to classify the energy width and spin parity of boron 9's first excited state, but have yet to agree upon any definitive results. We can look to the mirror nucleus of boron 9, beryllium 9, and get an idea of where the first excited state is supposed to be, but the fact that we're not seeing it there really throws into question whether the mirror isotope theory can be applied to these light neutron deficient nuclei. The reaction we're going to be employing to study this structure is boron 10 helium 3 alpha. We chose this reaction because the mirror reaction boron 10 T alpha has successfully populated the first excited state of the mirror nucleus beryllium 9, and also there has been success in previous years, in 1968 by Krofel and in 1988 by Arena, that roughly agree within their error bars. So we attempted this reaction at Florida State University at the John D. Fox Accelerator Laboratory. We used their tandem accelerator to produce a 24 MeV helium-3 beam, which was incident upon a boron 10 target that we got from John Green up at Argonne. Then the alpha particles from this reaction entered the split pole spectrograph, where magnets curved it into the focal plane detector and momentum separated the byproducts. Now, the focal plane detector tells us quite a bit. It gives us the energy lost within the detector. The residual energy is given by a scintillator that was positioned behind the detector, and it gives you a very accurate position, which tells you the magnetic rigidity and momentum of these particles. So we can take all these factors and get something that previous experiments in history didn't have, which is particle identity. So just taking the anode data, which gives us the change in energy versus the focal plane position, you see we have distinct particle groups. So down here are deuterons from any helium-3D reactions that occurred, and we're interested in all the helium-3 alpha products. So we can gate specifically on those and cut out everything else that we're not particularly interested in. We can also do this with the scintillator, the residual energy, and the anode, and get on some more specific particle groups. Then applying these particle identification gates on our raw data, we get a much cleaner spectra with distinct peaks that we are then able to identify. So in previous years, what a lot of groups were dealing with was just the raw data, where they had much higher background and had to discern their peaks of interest from every reaction that was happening. Now, another feature we had was double-sided silicon strip detectors positioned at backward angles, and we had those in place to look at the breakup products of boron 9. So as I mentioned, boron 9 is unstable and it wants to break up into 2 alphas and a proton. So we tried to see those breakup products with a delta EE DSSD telescope, and then look at those products in coincidence with our focal plane. And that is shown here, where this is the DSSD data in coincidence with our focal plane spectra. And this focal plane spectra is the same red spectra in this first image. As you can see, we didn't see much. It was mainly a lack of solid angle coverage and a lot of particle scattering in the chamber. So not much to be said at backward angles. However, this experiment wasn't a loss because we got lots of good forward angle data. we took data with our boron-10 target and also a lithium fluoride target as a calibrant every 5 degrees between forward lab angle 5 and 35. And from this data, we experimentally obtained angular distributions for both the ground state of boron-9 and the ground state of lithium-6. And then the lines in these images are DWBA calculations done with Ptolemy. Now we can further use this data with a collaboration we're doing with the LSU theory group, where they are giving us overlap functions from the symmetry-assisted no-core shell model. And then we'll take our analyzed experimental data and go from there. Now, we're still gonna try to look at boron-9 with some better detectors at backward angles. We want to retry this reaction with SABRE installed, the silicon array for branching ratio experiments. The lampshade shape of this array will give us a much better solid angle coverage. We're also going to increase the acceptance of the split pole, which will further increase our solid angle. And we're going to run the experiment with a thinner target, 50 micrograms per centimeter squared, as opposed to the 100 micrograms that we were previously using to allow for lower energy particles. And our hope is that by implementing these changes, we'll get a better picture of the coincidence and by extension, a better picture of the low-lying structure, boron-9. So lastly, I would like to thank the Department of Energy, the NNSA, and Centaur for funding this work, and all of my collaborators at FSU for all their help and use of their facilities. Thank you, and I will take any questions later.